Hi. Um, Thanks for having me here. It's not my first time in Japan, but I'm always happy to come back. I'm Clarence, and currently live and work in San Francisco. I got my degrees from Stanford, and I majored in artificial intelligence and data mining. Um, so today I'm going to talk about making and breaking machine learning anomaly detectors in real life. What does that mean? Um, Recently, there's been a lot of hype surrounding machine learning. Hype, as in there's been a lot of libraries published in various languages that make machine learning very easy to use, even for novices, even for people who may not be programmers. And why this is problematic throughout this presentation, we'll see. And we'll see how even for experienced developers, even for people experienced in machine learning, without the proper knowledge of how to use it in a security context, one might fall into a few pitfalls that will render it useless. Today, my goal would be to give an overview of machine learning anomaly detection, to spark discussions on when, how, and where to create these, and to explore how safe these are, how we can exploit these systems, and how these systems, when failing, will affect us. Then I'll discuss where we go from here, and that's it. So first of all, we have to define what is anomaly detection and what is machine learning. Machine learning, as all of you might know, are algorithms that are first trained with reference to input statistics, and then deployed on previously unseen input, and then you would make predictions as to what these new unseen input is. Anomaly detection can be seen as a subset of machine learning, and anomaly detection popularly uses machine learning, but in the past few decades, it has been using non-learning techniques. It's been using static rules, and it's traditionally heuristic-based, and so there's no learning involved. It is not dynamic, and it doesn't change over time. Anomaly detection can be seen as the predictive learning problem in machine learning, and as you can see, there's a small intersection between the two. So what kind of anomalies are we trying to find here? Intrusion detection is an important use of anomaly detection. And for the purposes of this talk, intrusion detection will be, broadly speaking, just anything unwanted in your system. For example, if you run a website, if you run a web server and you're serving one of the world's most popular pages, think Facebook or Google or Amazon, and you want to detect stuff that is unwanted. For example, if you have attackers in your network, if someone is trying to DDoS you and let's say your GitHub, you want to detect these anomalies and you want to be able to stop them. Or you want to be able to, even if you can't detect which parts of your traffic is anomalous, you want to be able to know that something is happening, and then you can deploy countermeasures to protect yourself. So machine learning, how can machine learning be used in this? These are some popular uses of machine learning that we have seen in the past couple of decades. On the top left-hand corner, you see Gmail. Gmail is one of the most popular email services in the US. I think it's the same here. And they have very vast knowledge in machine learning, and they have used it very successfully to protect your email accounts against spam. So this is a particularly interesting example because what's used to find spam in emails is commonly naive Bayesian models. And this is actually kind of ASCII text, ASCII art text, which makes it particularly hard to detect. Yet Gmail is able to find that this is spam. How does it do it? Obviously, it isn't looking for certain strings. It's not looking for the word Viagra, or it's not looking for other lewd words. It's looking for patterns in the text that humans cannot possibly code up in hard-coded examples. On the bottom left, you see credit cards, and the finance industry, the credit card industry, has also used machine learning very successfully to detect fraud. Also, they can detect if your credit card has been stolen. So talking to friends in the financial tech industry, I know that in the past they used to find if your credit card has potentially been stolen by checking for certain types of transactions. For example, if your credit card was used to buy a pair of shoes, and then shortly after to buy petrol or gas. Then they will detect this pattern as anomalous. But over time, as you might expect, the people who steal credit cards will know that this is going to trigger the system because the rule is static and it's not changing over time. So it's very easy for them to do something different to bypass the system. And that's why in recent years, credit card companies and banks have been investing a lot in machine learning to learn how the changing patterns of adversaries are affecting their fraud business and fraud detection. More generally, on the top right-hand corner, you see just time series data. Time series data can be anything that is generated in a streaming fashion by your system. For example, if you have a web server, then this time series pattern may be just the count of HTTP post requests or GET requests that you're seeing. And if there's any anomaly, you can see statistically the changes in the time series. And anomaly detection is something that is not as strict and has some level of fuzziness in it. So you can detect anomalies that you might find it hard to hard code. On the bottom right, you see botnets. So botnets is a very interesting problem, and this is where my day job lies. I work for a company in Silicon Valley that helps big companies fight botnets. And how it does that is by using a range of behavioral analytics, and then based on how you move your mouse, based on how you type keystrokes into a web page form field, we can detect if you are a human or if you are not a human. And this also uses machine learning to a very large extent. And yeah. So you might think a lot of companies will want to use machine learning to help make their products safer. How do you start? There are so many libraries out there, scikit-learn in Python, and there's also MATLAB libraries, there's R libraries, there's Apache Mahout. All of these make implementing machine learning libraries just 1 or 2 lines of code, and you can implement clustering in less than a page of text, which is unheard of in the past. Let's say you run a web server, and these are just Apache web logs or some kind of web logs that you see. How will you convert this into time series data? How will you convert this into a form of input that you can use in anomaly detection? And how would you find these anomalies? This is where we'll spend more time on later, and I'll talk more about different methods of doing this. First, let's see, why is machine learning good, and how does it compare with static methods? So the static methods I'm talking about here are, let's say, if you want to detect if someone is DDoSing you, and you do it by an IP and request count basis. So for example, if you see some IP address sending you more than 1,000 post requests in this minute, then you can block this IP address by defining a static rule. If any IP address sends more than 1,000 post requests in a minute, then you'll start to block him, you start to throttle him. This is very popularly implemented in all those WAFs out there, and we've seen how they failed over time. We've seen that attackers can very easily find out when they're starting to get throttled, and they can just scale out horizontally. This is because there's a strong feedback loop in this circle, and they know exactly when they're being throttled, so they can just fly under the radar, and instead of sending 1,000, they send 999, and they won't get caught. So machine learning is good because a large quantity of human work is often the alternative. If you have to think about how you want to take into account the fuzziness in detecting an anomaly that is hard to code in a few lines of code and rules, then you often have to spend a lot of developer time to develop a rule set that can cover all these cases. Machine learning is adaptive, which means if you perform online learning on streaming data, so when you're receiving traffic from your web server and your model is able to learn over time how your traffic patterns change, then your machine learning model is able to keep up with, for example, the increasing popularity of your website. It's able to learn when you're maybe running some promotions and your traffic sees an anomaly, but you don't necessarily think the anomaly is malicious. And lastly, it's able to discover unobvious statistical patterns and characteristics of the data that is not obvious. It requires minimal human intervention, theoretically, because you can just leave the model running and it'll be able to learn patterns that humans won't be able to code into the model. However, obviously, there's no silver bullet. Machine learning is not the right answer to every problem. There are many caveats and there are many specifics to using this solution in anomaly detection and in any problem, actually. So let's look at why threshold or static rule-based heuristics are good. So heuristics are good because it's easy to reason about. I think that's the top reason. When you have when you have a machine learning anomaly detector and you have an anomaly triggered, it's often hard to reason why your rule was triggered, what caused your anomaly detector to trigger, and it's hard to know exactly how your model has changed over time. But if you have static rule sets, you can find out exactly which IP address caused the rule to be triggered. You can find out just by ranking by number of requests made per minute of each IP. You can find out which IP addresses are the culprits. So it's simple and it's easy to implement, and it can also be dynamic but requires more work. So machine learning is interesting. I was here for the keynote this morning, and I thought it was really, really interesting how machine learning and artificial intelligence have evolved over time, and how there have been so many successful applications in machine learning that we see and use today in everyday life, whether we know it or not. Something that's really popular in the States and also here, I think, is Amazon. When you're shopping for something on Amazon, let's say you're buying some gardening equipment, and Amazon, if you scroll down, often recommends you products that you might want to buy. And this is a very prime example of how machine learning is being used to help a business. This is a recommender system, and how they do it is to build a profile of you. They build a profile of the customer, and based on how different customers have similar purchasing patterns, they recommend you what you might buy based on what other customers have bought, given that they were viewing the same items or they have bought the same items as you have. As I mentioned earlier, sorry for the profanity there, but just by looking at words in emails, you can very easily use the Bayesian model to detect how likely this piece of email is spam and how likely this is not spam. So we see using just some simple conditional probability here, you can use train a Bayesian model to tell with a certain amount of confidence how possible this email is a piece of spam. Something that is especially interesting, I think, is this thing. So what this is an English sentence. And English is not the most complex language, but if you think about it, it's hard to tell what a sentence means by using a computer and static rule sets. So what this is sentiment analysis. Sentiment analysis basically tells you, given a sentence that the system has never seen before, is this sentence good or bad? Is it positive or negative? So what this sentence is the movie does not care about cleverness, wit, or any other kind of intelligent humor. If you were to use a naive model, then there are many positive words here. Wit is positive, intelligent is positive, humor is positive, and cleverness is positive. But when a sentence is put together in a complex structure, then it's actually negative because of a negation in front, does not care about. So if you think about it, it's hard to code in a piece of hard-coded rules the specifics of the English language or any language. So what this does is it's a piece of deep learning software developed by Richard Sorter at Stanford, who is currently running a deep learning startup. And it's some kind of recurrent neural networks that can actually learn the patterns of the English language. And with just a small training set, it can very succinctly learn how sentences are formed and give you an accurate representation of whether this sentence is positive or negative. So we want to set expectations here. Machine learning has seen many successful applications and many successful solutions to problems in the past, as we've just seen. But what can it do for you in the security industry in particular? What can anomaly detection with machine learning not do for you? When is it helpful and when is it not helpful? I started on this research because I organized this meetup group in Silicon Valley. It's called Data Mining for Security, Data Mining for Cybersecurity. And it's a largest gathering of data scientists and security professionals in Silicon Valley. And I've been talking to people about what they've been doing in their work and what kind of new stuff that they're implementing and what new projects that they're embarking on. So I started this project because I realized that there was a kind of a weird problem. There are many machine learning and anomaly detection papers in academia. There's a lot of research being done in this area, but there are not a lot of successful systems in the world. Usually when something has a lot of research put into it, and research says that this works very well, and then soon after you'll see there are lots of commercial solutions to it. And even if there are no commercial solutions, there will be open source solutions. There will be very easy to implement and integrate tools that you can use. But we don't see that for anomaly detection. Why is that? We end up seeing people trying to implement their own in their companies, and many people are doing that. They try to implement their own anomaly detection systems. They often use machine learning, and it's because it's hard to understand whether they've gone wrong or not. It ends up wasting a lot of their time and the organization's time and money. So we'll see what the difference is. The big machine learning and anomaly detection problem is that machine learning's strength is to identify patterns. It's to identify similar things. So you want to find what is similar to what's previously seen without describing the activity upfront. And machine learning used in recommender systems, spam detection, natural language understanding have seen great success. But in the security industry, in anomaly detection, it's different. I'll point out some fundamental differences that makes it much harder to integrate. So a classic scenario where machine learning does very well is when you have K clusters and you classify unseen entries into clusters based on comparing the similarity of each of these data points that you have. And this is, of course, KNN. So K nearest neighbors, which is a very popular and simple and easy to understand clustering mechanism. So the basic rule of machine learning is that you have to train a system with specimens of all classes. If not, you'll have a class imbalance problem. And when you have to train it with all classes, what I mean is that you have to train it with a comparable number of positive specimens and negative specimens. In the case of anomaly detection, this means that you have to train it with anomalies and you have to train it with non-anomalies. And if you think about it, that doesn't make sense. Because what makes an anomaly an anomaly statistically is that there are fewer anomalies than what's the norm, without taking any contextual knowledge into consideration here. So spam detection and anomaly detection or intrusion detection are different problems because you're training on both spam and ham. You're training on both positive and negative specimens mixed together, and you have very little negative specimens. So there's the inherent class imbalance problem here, and that's why. So what makes anomaly detection so different? So here are some of the points that I'll go into detail each one of them. And then we'll see how to implement an anomaly detector, and we'll see how to exploit one. So anomaly detection systems have a very high cost of error. If you think about it, machine learning systems actually learn by trial and error. They learn by making mistakes, and then through reinforcement learning, their model strengthens over time as it's seen more and more positive or negative examples. So compared to other applications, it is very intolerant to errors. If you think about Amazon.com, or Gmail. If the system recommends you something that is totally irrelevant, for example, when you're buying a spade, it recommends you a car steering wheel cover. So it's not relevant, maybe, but you don't care about it. You think, okay, so what if they recommended me something? It doesn't affect me, my life. If you receive a piece of spam in your email inbox, then it's not the end of the world, because you can just mark it as spam. You're helping out the system to learn, and this is exactly the error that the Gmail system is making. And when you help to classify it as spam manually, you're actually helping make the overall system better for everyone. So anomaly detection systems are intolerant to errors because let's say you have an analyst that receives the reports of anomalies. Every time an anomaly is triggered by the system, someone somewhere receives an email or a call in the middle of the night. So I'm not sure how many of you have received these emails, but I've been receiving these emails at my workplace all the time. Actually, I'm still receiving them now. And sometimes I just have a Gmail filter. I just mark them as read or just delete them automatically because it's too annoying, and a lot of the time it means it doesn't work. So once there's too high a rate of false positive or false negatives, it's very easy for the operator to distrust the system and to think that any anomaly that it flags is unreliable. And compared to other machine learning applications, this is fundamentally different. The second point is the lack of training data. So what data do you train your model on? I learned this the hard way by implementing the experiment here, and I realized that when you're looking at input data, it's often hard to identify the bad points in the input data so you can clean it. Because when you train a model, depending on which model you choose, you want to separate the classes. You want to if you're using supervised learning models, you want to be able to classify a goal set of what is positive and what is negative. Then you can train a model in a supervised way well. It's hard to clean this data because if you're able to, with accuracy in real time or over a large set of data, determine what is good and what is bad, then you don't actually need the anomaly detection system in the first place, right? So next, I'll talk about the semantic gap. The semantic gap is something that is very special to this problem. I talked about it earlier. When you get an alert, why did you get the alert? How do you determine if this alert is really something that you should be worrying about or not? With static rule sets, as I mentioned, it's easy to find out who triggered the alert and how the alert was triggered. But with this learning model, especially if it's constantly changing, then it's hard to determine, because unless you keep a snapshot at each point in time of the model, it's hard to determine how the model looks like over time and how it changes over time. So something I want to talk about is why the model changes over time. The model changes over time because you want to take into account the changing nature of your traffic. A large reason why someone would use a machine learning model over static rule sets is because with a machine learning model, the system can take into account changing modes of traffic. So let's say you're running a website, and giving the same example earlier, you have promotions once in a while. Let's say every Monday you run a promotion. And then during a promotion, presumably, your traffic will spike, and then you'll see a very characteristic pattern of what happens during this promotion. And when you have a static rule set, it's hard to take into account every small detail of how your traffic looks like over time. And let's say the good thing happens, your website gains a lot of traffic gradually over time. This is called drift. And this drift is really what breaks static models, because when your website's notion of normality changes over time, then it's really hard to define static rule sets that can change along with this model and to detect how these models change, how much these models change by. The second last problem of machine learning anomaly detection is the evaluation problem. Defining a sound evaluation scheme is much more complicated than building the system itself, especially because if you could define what's good and bad in the first place, then you don't need a system. So a lot of anomaly detection research papers have evaluation problems, in my opinion, because they use the same piece of data set and they train their models and they use the same test set. So reading about 24 papers, about 23 to 4 anomaly detection papers using machine learning, I realized that they were all using 2 or 3 data sets from the 1980s. They're both origin destination flow or they're Department of Defense in the US. They're data sets from then. And this is precisely because it's so hard to obtain a data set that's reliable, and researchers need a basis of comparison between academic papers to compare their algorithms against. So this is very different from implementing something in the real world. Machine learning is something that's very context specific. So if you're looking at different input data sets, even if the problem seems very similar on the surface, the optimal solution that you might choose in the end is very different. For example, if you're recommending someone products on Amazon, and if you have a video watching website like YouTube or Netflix or Hulu, and you want to recommend them videos, these problems seem very similar, but they actually have very different solutions for how they're actually implemented. Because the nature of the problem is different, the way someone chooses when to watch a video and what product to spend money on is very different. So even though these two problems seem similar, the optimal solution is actually the opposite of each other. Lastly, I'll talk about the adversarial impact. If you think about it, running a machine learning model that changes over time will be susceptible to attacks by adversaries. People who want to break into your system will spend time and effort to bypass the system. If you have a static rule set, then they'll fly under the radar by not triggering your rules and by sending, for example, a number of requests that is just below what will trigger the rule. If you have a machine learning model, it's slightly more complicated, but it's very exciting, and it's what a large part of my presentation will be on. Advanced actors can and will spend the time to bypass your system, and here we'll assume that they have global knowledge. So we'll assume that they know your system is trained with, for example, a clustering model. They know that you're training it weekly or monthly, because really there are only a certain number of permutations of this that they can go through before they get this knowledge. So how have real-world anomaly detection systems failed? I mentioned before, these systems often have many false positives. And once this happens, then it's basically useless. It's hard to find attack-free training data, and it's used without deep understanding. So the problem of use without deep understanding is an interesting one. One might think that when you have more and more libraries out there that make machine learning easy to implement and easy to code and easy to integrate, then it might be a good thing. But I would argue that maybe it's not such a good thing, because if you have, let's say, a function for clustering and for SVMs, and you are using just a function that you found in scikit-learn, and then you have many parameters in the functions. I look at these parameters and I'm thinking, I think I'll just use the default because I'm not sure what each of these mean. What people don't realize often is that changing each of these parameters will often turn the problem on its head. For example, if you use a Gaussian kernel or if you use a linear kernel, then it might be totally different results. It will give you a totally different model in the end. Lastly, there's model poisoning, which I'll talk about later. So is machine learning and anomaly detection hopeless? I don't think so. I think it's more important to understand your application and to understand why you're using machine learning in your problem. Would you be better off using static rule sets, or would you really need the functionality that machine learning provides? You need to acquire a deep semantic insight into the system's capabilities and limitations. Rather than treating it as a black box, just using functions that you saw in a code example somewhere. So let's see how to do it. For this example, I'm going to use the case that you run a website because it's simple. And then you want to detect when someone is DDoSing you. So this is something, it's a very simple example, and many industries see the same kind of patterns. So first of all, you want to generate a time series. Then from this time series, you want to select representative features. Then you want to train what's normal, and you want to alert when there's any deviation from normal. This is an example infrastructure. So on the left, we see the data sources. And this data sources, in this case, would be your web logs. So for example, if you have Apache web logs, each of these can have the IP attribute, the URL attribute, the HTTP method attribute, and can also have timestamps and perhaps other more detailed attributes. And from this, you have to find features. So feature generation is something that is complicated and we'll look into later. And it actually can make or break your algorithm. And an example feature would be IP and count. So this is an aggregated feature. So you basically count, let's say, over 1 minute, today from 4 o'clock to 4:01 p.m. How many requests were made by this IP? How many post requests were made by this IP? How many GET requests were made by this IP? Then there are also many examples of this, as you might imagine. So how do you choose a subset of these features? How do you weight these features such that a combination of these features per data point would give you a good representation of your input data? Secondly, you want to construct the time series. And by constructing the time series, what I mean is that you have to generate different time series and construct a very robust model of your streaming data. And feature selection can also be done in an automated fashion. We'll dive into one later. It's called Principal Component Analysis, or PCA. And this is something that is used widely in anomaly detection. Okay, so, and then after that, we'll go through manual validation because it's just, if you're just using statistical methods to validate these models, then there's often too many false positives. So in most real systems, there's often a human in the loop looking at all these anomalies generated and then deciding manually whether they are real anomalies or not. So common techniques for machine learning, there are some density-based techniques, clustering, support vector machines, subspace correlation-based. I won't go into all of them because there'll be a year of machine learning work. But I'll focus on clustering because it's easy to understand and because it's easy to implement. I mentioned k-nearest neighbors earlier, and that's a method of clustering. And there's also a lot of other methods like hierarchical clustering. There's random decision trees. So yeah. So I mentioned a lot about the model earlier. What is this model that we're talking about? Here I have a simple example of a model. This is a simple two-dimensional model. There's only the x and y axis. Let's call them the x and y axis for now. And there are clusters formed. So for each and every input data point that you see, so in your time series, this would be each and every request that's made, or in the case of IP count, it will be each and every IP count per minute. You will see that each entry point actually corresponds to a point on this two-dimensional graph. So these are called centroid clusters. The different colors of points are artificially colored because they are obvious clusters, and depending on the algorithm you choose, this means that the distances between them are small enough that you can classify these points as similar. And if a new point were to come in, let's say a point were to come in right there, then you'd see that this is an anomaly because it doesn't fit into any of the pre-defined clusters you have there. So it's a statistical anomaly based on the features that you selected. But is it really an anomaly? There's no easy answer to that because it could just be that the features that you chose, the two features that you chose, x and y here, might be irrelevant, or they might not be able to capture the notion of normality that this new point that's in the center of the graph has. So even though that's a statistical anomaly, it might not mean that it's a true anomaly. So centroid clusters are good for online learning because as new points come in, you can just add to the graph, and as you can see, storage and memory will be worst case O of n squared. And because you just have to calculate the distances between between the new point and each of the new points, and you can maintain a constant ongoing learning model of your input data. And so if you want to maintain only, let's say, the last week of data or last month of data, then you can just eliminate old data points as new data points come in, and you can do various optimizations on this. This is a very, very well-researched topic, and I won't go into this. So how do you select features? Earlier I mentioned that for the simple web server example that we're talking about, there are some obvious features to select. But let's say you have a more complicated problem that few people have seen before. You run a very special business, or for different security applications, it is often the case that your particular application has something that no other application has. So how do you select features? How do you know which is a relevant feature? And how do you choose a good combination of these features? Isn't it just a parameter optimization problem? So thinking about it, you don't have to deal with the complexity of machine learning anomaly detection techniques. You can just use a simple rule and detection engine to alert when data points that do not fit the expected trend line arrive. There are too many possible combinations to iterate over. It's hard to evaluate, and there's a frequently changing optimal. So thinking about just a simple example of weblogs, there are so many different permutations and combinations of features and weights for each feature that you can use for this model. And then it's hard to evaluate because performance accuracy is not the only criteria. Even if you could accurately determine if this model were optimal or not, maybe you're looking for something that performs well, but not as well as the other one, but it is easier to explain why this happened. So there are shorter training times. Shorter training times might be a very important criteria, because if you're running an online learning approach, let's say your web server receives 1 million requests an hour. And if you're using an O of n squared algorithm, you might not be able to keep up. You might need a supercomputer to compute this anomaly things. So you might want to look into something that's more optimized. And you want to reduce overfitting. You want to be able to train a model that's generalized enough. Let's look at principal component analysis. So principal component analysis is something that can help you to automatically select features by transforming the data into different dimensions. So let's say your data is two-dimensional. And on the left, you can see the x and y dimensions. And on the right, you can see principal components. So what this means is that if you just think about moving the x and y axis instead of moving the points, then you want to find the x and y axes that can give you the maximum variance capture. And variance capture can be seen at the bottom. You see PC1 and PC2. PC1 is principal component 1, and PC2 is principal component 2. Sorry if you're bored by this. But this is the optimal. When you see that principal component 1 captures the most variance when most of your statistical points are furthest apart. This is the same example in a three-dimensional space. You basically rotate three orthogonal principal components such that you want to find the optimal one, and the optimal one is here. You can see PC1, PC2, PC3, and PC1 captures the most variance. And this principal component analysis algorithm is optimized such that it's compute efficient, and it can help you to find the principal components faster. So you want to choose principal components that cover 80 to 90% of your data set's variance. Why is that? The fewer features that you have in your learning algorithm, the more efficient it is. Because the fewer components it has to calculate closeness to for. So for example, if you're defining a linear model and you want to find distance between 2 points, if you have to rely on 1,000 different features, then you basically have to calculate what the values of these 1,000 features are, and then calculate it for the other point and all the other points in your system, and then compare the distance of them. If you choose only 2 features, and these 2 features are excellent, these 2 features can tell you exactly what this data point means, then you just have to calculate 2 features for each data point, and that's good. So this is a scree plot. Scree is just a name. You see when the number of principal components is used is small, but the cumulative variance capture is high. Then you see the green line is actually an optimal use of principal component analysis. So how do you avoid common pitfalls? You have to understand your threat model well. You want to keep the detection scope narrow, and you want to reduce the cost of false negatives and positives. Because like it or not, there's going to be false negatives and positives in these systems because it's machine learning. So you want to know what do missed attacks cost. So if there's an attack that comes in and your model is not able to tell that it's an attack, what is the consequences? What concerns do evasions pose? You want to keep the scope narrow because machine learning is not a silver bullet. So don't start with the premise of using machine learning. Use it as a means to an end, or just to find rules that you can use in static sets. And we also want to close the semantic gap. This is a cute picture. I think it's somewhere in Canada. And just two bridges that started off from both sides of the shore. And there's this gap here. So with machine learning models, you really want to be able to understand it, because if the system gives you a result that you're not able to understand or evaluate, then what use is the system? So we'll spend a short time on evaluation techniques. How good is your anomaly detector? How easily can you find false positives? How easily can you insert another contextual layer that can filter out the statistical anomalies? So for example, the example that I mentioned earlier, if you have a new point that comes in that's far from all the other clusters you made, how can you have another layer in there, whether it's a human or whether it's another contextual verification layer in there that can tell you if this is just a statistical anomaly and not a true anomaly or not. There's this interesting anecdote that I like to go into here. You don't just have to evaluate false positives. You also have to evaluate true positives. So let's say you have a system that has 99% accuracy. But if you don't understand why your system performs this well and how you get the results that you're getting, then it can be meaningless. So there's this famous happening in the US Department of Defense in the 80s. They were basically trying to use deep learning, which was the hot topic then. It was neural networks was the hot thing then. And so they're trying to classify 2 sets of pictures. Let's say they have images of tanks and they have images of cars. And they feed the model, the deep learning model, these images of tanks and cars, and then it tells them, okay, this is a tank, this is a car, this is a tank, this is a tank, this is a car. Then it gives the model new unseen pictures. And classic machine learning problem, it's supposed to tell you if this new picture is a tank or a car. So they published a paper that said, this is wonderful. We got 90+% accuracy, and we believe that this is a perfect deep learning model, and we can use this in our tanks in the future to detect if this is a civilian or this is an enemy. They retracted the paper. It's kind of funny. Can someone guess what the model was trained on? Okay, sorry. So on the left, you see pictures of tanks. On the right, you see pictures of cars, different cars. So the model actually was training on the different pixel colors that were coming in. If you see, there's a lot more bright colors in the tank photos and a lot more dark photos in the car photos. So if you were to give it a tank on a road or with a gray sky, then it is very possible that the model would have told you it's a car. So even though this model performed very well in the training set and the test set, it wasn't a good model because it didn't capture the essence of what you were trying to do. So lastly, I want to attack a model. So what do I mean by attack a model? There are 2 things that I'm trying to do here. The first thing is to manipulate this learning system to permit a specific attack. So for example, if I want to perform data exfiltration from a particular system, and I know that the anomaly detection system is going to catch me because usually people don't just do a SQL dump of my database. So I want to be able to change the anomaly detection system such that this will not be marked as an anomaly. So the second thing is to degrade performance of the system and to compromise its reliability. You can do this by methods that I've talked about earlier. So if the system generates lots of anomalies, lots of false positives, lots of false negatives, and generates 1,000 alerts an hour, then the operator is going to be ignoring all alerts from this system. So that's a way to degrade performance. Chaff is an important concept in this area. So chaff is actually used, is the English word used to describe the smoke that comes out of the back of airplanes, and it's used to deflect homing missiles or to confuse homing missiles. And this is exactly what we're doing here. We're inserting chaff into the machine learning model, and we're trying to confuse the model. We're trying to make the model think that, okay, maybe this new point inserted is normal, and when we insert a large amount of chaff, enough amount of chaff, then we're able to change the model. So here we see we have a very naive decision model here, the decision boundary here. The decision boundary is defined by if a point lies outside the decision boundary, then it's an anomaly. If it's within the decision boundary, then it's not an anomaly. So this is just a very simple distance. And the distance of the blue circle to the boundary is just, for example, Levenstein distance or a kind of threshold that you use to define what's anomalous and what's not anomalous. And so chaff can theoretically help you to shift the decision boundary in such a direction that benefits you. Another kind of chaff is when you have a lot of this in all different directions. And what you're basically trying to do, for example, this is commonly used in DDoS attacks, is when you insert chaff in all different directions, if you just insert traffic that is unpredictable and is all over the place, then you can see that the decision boundary initially is small, but then it became big. So the operator of the website, it's hard for you to know if this is due to organic traffic. Maybe you're just getting visitors from all around the world all of a sudden, or maybe your traffic, or maybe there's something wrong with your time series generation. So it's hard for you to know what's the cause of this problem. And if you're seeing chaff like that, then you're basically degrading the integrity of the system. So if you think about it, isn't it easy to detect when someone is injecting a lot of traffic into your website? Exactly. So that's why people have come up with the boiling frog attack. So the boiling frog analogy is when you put a frog into cold water and heat it up slowly, then it won't actually jump out. I'm not sure if this is true or not, but they say if you put a frog into boiling water, it'll jump right out because it'll be able to know that it's in trouble. So to avoid detection, similarly to this analogy, you go slow. Instead of inserting chaff at a very high rate at once, you insert it slowly over time. So for example, you insert 10% of your total chaff today, and then next week you insert 20%. Following week, insert 30%. So it looks like it's organic. You want to mimic what's natural to confuse the operator. So how would you defend against this? Let's just go quickly and talk about how some possible solutions. You can maintain a goal set, a test set. So before you run your system, before you deploy it publicly, you can have a goal set that can basically tell you what's good and what's not based on a certain test set of data that you have. And then after running it for a month, you test it again and you see how it's changed over time. And if it's changed too much, maybe someone's attacking you. But how do you know it's not just organic change? The next thing is decision boundary ratio detection. What do I mean by this? So if someone's injecting chaff, the more efficient way that they'll do it is to inject chaff close to your decision boundary because they don't want their chaff volume to be detected as anomalies. They want to go slow and go gradually. And so if you can detect the ratio of your traffic that is falling into this certain decision boundary, then maybe you can detect when someone's trying to attack you. So can machine learning be secure? I would say it's not easy to achieve for unsupervised online learning because the learning conundrum, the learning paradox is that with no contextual knowledge, it only uses statistics to make decisions that are inherently strongly context-based. You can make it much harder for the adversary, though. You can slow them down, and it gives you a chance to detect when something's going wrong and then perform a review. So there are many defenses proposed for this. There's antidote, which uses the median instead of the mean, because obviously median is a much more robust, it's a much more secure way of finding variance, and PCA actually is not designed for security. It uses the mean, it maximizes the mean. So you have to use the appropriate distribution as well. Not everything is Gaussian. Some things are linear, some things are Laplacian. So you want to be able to understand your data model well and then choose a proper model that represents it. So this is what I mentioned earlier. You want to find an appropriate distribution for your data set and to really understand your input data and then understand your threat model and know what you're looking for. So lastly, I'll go into this. I'll go into this section. I ran my own simulations with some real data. What I did was I implemented some anomaly detection systems based on papers out there. So what's considered to be the latest and have the best results in research papers. I just implemented these, and so I had fine-grained control over which parts of the algorithm I was using and which parts I was not. And then I had I downloaded some large data sets from various sources. So it might be a bit faint, but all of these are dots that are plotted. And this is a 10% subset of input data that I chose from input Apache server web logs. The y-axis is the projection onto the first principal component. So note that I use PCA, and I chose only the first principal component. So the first principal component actually captured about 67% of the variance, which is pretty good for a real-life data set. And so you can see there's some kind of trend here. This is just a simple linear regression model trend line. And you can see robust PCA and naive PCA. So naive PCA uses just the very standard way of feature selection. And robust PCA uses methods that are, for example, it uses a Laplacian model, and it uses maximized absolute deviation. And so I injected some shaft here. This is a simple shaft injection, and just to see if it would change these trend lines. By the way, generating this shaft is hard. I had to go through a long period of trial and error because it doesn't. I can't tell what a new data point would end up, where the new data point would end up. I'd basically have to insert new data points and then have to see where it ends up and then tweak various parameters of the input data such that I can generate shaft in a particular area. And we can see that it did move. The faint lines are where it was originally, and the dark lines are where they are now after this shaft injection. Robust PCA generates a smaller shift, and naive PCA generates a larger shift, which is expected, because it uses median instead of mean. And then I have a simple detection logic. So if I see that more than 10% of the data coming in is classified as anomalous, then I'll detect it. So this is just some simple detection logic that you can use to detect when someone is trying to poison your model. And to defend against that, I have some training periods here. So over training period 2, 4, 6, 8, and 10, I injected various levels of shaft. And you can see by the different colors from green to red what points I injected at which training periods. And this is the other model when I'm injecting so much shaft that I'm just confusing the model and to shift the notion of normality and to expand the decision boundary. So you can see it shifts quite a lot as well. And this is a graph that I want to go into some detail. So the ideal case is when you have very low false positive rate and very high true positive rate. So the ideal case is a 90-degree line from here to here. And a random detector will give you with 50% probability will just tell you with 50% probability that something is an anomaly or not. And this can be seen by the middle line here. So as you can see, when the plots approach the 90-degree line, then it's a better detector. If it approaches a random detector, then you know it's been compromised. So robust PCA with 30% shaft, which means that 30% of the total traffic that this anomaly detection system has seen over the training period is injected by adversaries. Then it ends up here. When it's 50% shaft, it's further weakened. But then detection was tough because when you're injecting 50% of the traffic that the operator sees over a training period, then you can guess it's pretty easy for the operator to find out that he's being attacked. So using a boiling frog attack is a pretty good compromise. And you can see the blue line there is the result of a boiling frog attack on RPCA. So evasion successes. For robust PCA using boiling frog injection, we can see that there's a 38% evasion success, which in my opinion is pretty good, because if I were to just extend the training period and to extend the attack period, then I can push this number much higher. I was using a 10-week training period and about 100,000 lock set. So the 50% shaft injected, I got 38% evasion success. And if 4 in 10 attempts at an attack on your web server goes through, then I'd say this anomaly detection system was a failure. So anomaly detection systems today are not so good, but they're still improving. Pure machine learning-based anomaly detection systems are very vulnerable to compromise. So if you were to use machine learning, if you want to build an anomaly detection system from scratch, which a lot of people want to do, then I actually recommend you to start off by listing down what you're looking for, what kind of anomalies you're looking for, and to weigh both methods, static methods and machine learning methods. You want to find features and thresholds using machine learning, and then code that into static rule sets. And then you use those static rule sets so you can get both benefits of a machine learning model and a static model. And then you can retrain these features, you can regenerate this set of features every so often to take into account the drift that your traffic might be seeing. So what next? I want to do more tests on anomaly detection systems that others have created. So far, I've been running tests on my own ideal models based on research papers that have promised good results. But there are some open source solutions, and there are a lot of vendors out there that are offering machine learning anomaly detection. And a lot of them have varying levels of efficiency. I want to try other defenses against pointing techniques and also experiment on more resilient machine learning models. So lastly, I mentioned earlier that I run this meetup group, this user group in Silicon Valley, data mining for cybersecurity. It's been very successful. We have over 1,000 members so far after only 6 months, and we have a meetup every month where big companies like Facebook, Google, LinkedIn, and Netflix have came to present. Their security teams are talking about how they use data mining and machine learning to solve problems. So I think this is beneficial to all communities, and if you're interested in starting a meetup group like this in Japan or a chapter here, feel free to come to me and we can talk about it. That's all. Thank you.
ありがとうございました。質疑応答とさせていただきたいと思いますが、お時間の関係でお一人だけ、お受けしたいと思います。質問ございます方、挙手をお願いいたします。じゃあ前方の。
Thanks for the presentation.
Yeah.
You mentioned about the lack of anomaly data as part of the problem in anomaly detection, but isn't it possible to ask such a penetration vendor to provide such anomaly data since they have tons of it for sure?
Yeah, so that's a good point. There are two minor issues that I see with this. So for one, you have to ensure that the positive test class, the positive training class is truly positive. And it's hard to ensure that because when you're running a web server, there's bound to be anomalies that you're looking for that you haven't detected. And so if you include that into your positive training set, and even if you have a very large volume of negative training examples, then the model will still not be ideal. And the second case is that there are just too many, by definition, there are too many examples of deviation from normality. So let's say you hired a pen testing team to attack your model, and they generate a text in some certain way. So the notion of normality is quite narrow, but the notion of abnormality is very wide. So there's just so many ways that that traffic can be classified as abnormal, and it's hard to really train a machine learning model to capture all that abnormality. Yeah.
はい、それではこのセッションを終了させていただきたいと思います。どうもありがとうございました。